Fusion, and the potential for zero carbon emission energy. So you've probably heard of the nuclear fusion process. Usually this is confused with nuclear fission, which is used in nuclear reactors today. Or you've seen it muttered by a mad scientist in a movie, talking about cold fusion. But that is not the case. Fusion is the process by which the sun produces the light and heat that all life on this planet requires. Fusion is the process of taking one lighter atomic ion and a heavier ion and compressing them until they fuse to make a new atom. During the creation of this fused atom, neutrons and energy are released. The most common occurrence of this is when deuterium and tritium, a lighter and heavier hydrogen ion, are fused together to create helium, releasing one neutron and a lot of energy, which follows Einstein's famous equation. This is the process occurring inside the sun, and the current process the scientists have successfully completed to date. You might be thinking, so how could this work on Earth? The sun is pretty hot. And you would be correct. This process is completed in the sun at a temperature of 15 million degrees Celsius. For this process to run on Earth at an optimal capacity, the reaction would need to occur at roughly 10 times that temperature. This is because the pressure at the sun's core is not safely achievable on Earth. This is one of the major issues that limits the development of this technology, but scientists have overcome this by the use of two separate methods: the magnetic cage method and the inertial confinement method. The magnetic cage method uses strong magnetic fields to contain and prevent the particles from escaping the reactor core. This allows for the core to reach the temperatures that this process requires, without coming into contact with the reactor structure. Instead of magnetic fields, the inertial confinement method uses high-powered lasers to heat and compress fuel pellets. These fuel pellets contain the deuterium and tritium ions. The lasers heat the outer layer of the pellets to extreme temperatures until it explodes. This then drives the interior layers inwards, increasing their density and temperature in a fraction of a second, causing fusion. This reaction occurs so fast, it doesn't allow for the ions to overcome their own inertia, thus inertial confinement. I know, this all sounds great, but it's nuclear power. What about when all this fails and melts our faces off? Well, it is nuclear, but the safety issues that alarm the general public with nuclear fission don't exist with nuclear fusion. Unlike fission, the fusion reaction doesn't occur in a chain reaction form. This means that the reactor meltdown associated with fission isn't possible. If there is a breakdown in the supply of fusion fuel, the plasma will cool within seconds, and the reaction will die off. Well, what about radioactive waste? Fusion does produce radioactive products from the impact of extremely energetic neutrons with the walls of the reactor. But these products are shielded from the environment outside the core, and after their use, they are collected and safely stored until they decay, with a half-life of lower than 10 years for most of the products. Well, it's great that we have options for how to create fusion energy, but how does this compare to the options we already have? The current cost of ITER, the 500 megawatt plant being built in southern France, is estimated to be around $20 billion. However, once the technology has advanced enough, the costs will be greatly reduced. As you can see from the graph, comparing the projected capital costs of a fusion power plant, it is only slightly more expensive than most of its competitors. This means, in the future, the initial investment of a fusion power plant is equivalent to already available options. When comparing the levelized costs of electricity, the cost of fusion electricity is almost double most of its competitors. This is an issue that will hinder the use of this technology, but looking at a standard technological learning curve, this price should be driven down over time. For the most important comparison for future generations, the overall carbon intensity of fusion is much less than its fossil fuel competitors. And when comparing it against renewable competitors, the carbon footprint due to its construction is similar. We have already discussed the extreme conditions that scientists are currently struggling with in order to initiate thermal nuclear fusion. the energy source of stars. So far, attempts at creating this reaction are limited to around a minute, which confirms that it can be done. However, the energy output is yet to exceed the energy input from either method. Making this work in a lab is different than actually sustaining this reaction long enough to create deliverable energy. This seems somewhat of a pipe dream, and the common phrase passed around the fusion community is that fusion is always 30 years away. There have been many advances since fusion's inception in the 40s and 50s. In considering that scientists of that era determined that fusion was unattainable, we now see the slightest glimmer of hope that in fact this technology will successfully be developed. With the recent successes in various labs around the world, as well as the collaborative effort on the ITER tokamak reactor being currently constructed in southern France, there is a lot of optimism pushing us towards this major energy breakthrough. Will we see this breakthrough in our lifetime? Perhaps, but we might have to wait 30 years.